Let's now look at our second example. Here we have a differential equation, third order, and we want to find the Laplace transform of the response y of t for the initial conditions of y initially being 6 and y dot and y double dot being a 0. What are the fundamental ideas here? Well, the Laplace transform of y, we're going to give that a name. This is a definition of being y of s. The Laplace transform of y dot, that's s times y, minus our initial condition on y, so that's s times y minus 6. Laplace transform of y double dot, got s squared y, minus s times the initial condition for y, minus the initial condition of y dot. For this problem, y dot initially is a 0, so this becomes an s squared y minus 6s. Laplace transform of the third derivative, we just do it one more time. The core part here is s cubed y minus s squared initial condition on y minus s initial condition on y dot minus y double dot initial. Well, both of those for this problem are a 0, so that Laplace transform is s cubed y minus s squared times 6. And finally, the Laplace transform of the right-hand side, 5, that's a 5 over s. So I put all these together. These are fundamental ideas. These are coming from page 2. Keep those in mind as you do that. Do it. Think about it enough you don't have to look up those relationships each time. And that gives us a fairly straightforward approach here on getting the Laplace transform of our variable of y. So we take the Laplace transform of the equation of motion. The y triple dot becomes s cubed y minus 6s squared. That's the first term. The next one's at 2 times the transform of y double dot. We have a 3 times the transform of y dot, that's sy minus 6, plus 4 times y, and that's equal to 5 over s. So if I group together the coefficients in front of y, I get an s cubed, I get a 2s squared, 3s plus 4 times y. Everything else going on the right-hand side gives me a 5 over s plus a 6s squared minus a 12s, which becomes a plus when we bring it over to the right-hand side, and then a plus 18 as that. So the last step then is to produce our fraction here, where y of s, which is the Laplace transform of the response y, is 5 over s plus 6s squared plus 12s plus 18, all divided by s cubed 2s squared 3s plus 4. So that's what our goal is. Laplace transform the whole thing. Use the important relationships there on page 2. Let's check our work. And actually use a little prediction here too. That check and predict will be using the initial value theorem and the final value theorem. So the initial value for y, we know what it is. Let's make sure that we can recover that. It's the limit as s goes to infinity of s times y of s. So what we have here is a 5 plus 6s squared plus 12 s squared. This should be an s cubed here, so I'm multiplying it by s, plus 18s, s cubed plus 2s squared like this. Again, we're taking the limit here as s goes to infinity to find the initial condition for y here. So I'll use the same ploy I did before. I will get everything here in terms of fractions of s. So I need to factor out an s cubed from the top. I get a 5 over s cubed plus 6 plus 12 over s plus 18 over s squared. In the bottom, I'll factor out an s cubed also, because I want everything in terms of either a number or a fraction on s. So that's 1 plus 2 over s plus 3 over s squared plus 4 over s cubed. And the reason for doing it in that way is that when I make s large, make s go to infinity, I know this goes away, that goes away, that goes away, as well as all of these terms like that. S cubed over s cubed, that goes to a 1. And so in the end, all I have left is a 6 on the top, a 1 on the bottom, 6 over 1, that's 6, and that checks out. Again, we knew that, but we're just doing our check here to make sure that our transformed variable has that. The final value theorem, similar kind of thing, except we take that and let s go to a 0 in that case. So if I take the result up there, that's going to be the limit of s going to a 0 of 5 plus 6s cubed plus 12s squared plus 18s divided by s cubed plus 2s squared plus 3s plus 4, and letting s go to a 0 loses that, loses that, loses that, that, and that. We have a 4 left on the bottom, we have a 5 left on top, and we get 5/4. We did not know that. And this is a rather profound, I think, usage of the Laplace transform. The point I think we made at the beginning was the Laplace transform approach will oftentimes allow us to understand some qualitative nature of the response without actually even solving. We haven't done anything yet in terms of inverse Laplace transforms, partial fraction expansions, finding residues and things like that. But yet we know that if you let time go to something large, the steady state value for y is a known. It's 5/4. Fairly profound observation from using very little information about the response.